talk a little bit about scattering again, just very briefly. When we're talking about wave packets, there's another way to look at it. The derivation I gave was okay, but the other way to look at it, if you sort of go back to the first thing I mentioned at the start of the section regarding the cross section, that you can relate it to the number of particles that are hitting the detector. And that would be sort of the initial number of particles that you're sending in times the probability that any one of them gets scattered into a solid angle. And this is multiplied by that solid angle that comes in. And this probability itself, you can think about it as the area subtended by that solid angle times the initial velocity of the particles, and then this is the kind of the probability integrated over all times for the scattered portion, because this probability is the probability you get scattered into a particular solid angle. You're sort of assuming that you're detecting things away from the incoming direction, that it's in some solid angle that's sort of away from the initial direction, so you don't capture any of the incoming guys that didn't get scattered. And so if you plug that in, you can kind of, you plug in for the scattering solution, you do that kind of stationary phase approximation, or rather you expand the integral you have for the scattered wave function, the time dependent one. Remember that this thing is a Fourier integral of an envelope that's sort of centered around K0, the incoming momentum. And then you have the stationary scattered solution, the stationary one, the one that we solved in class with like the spherical wave and so on. And then the time dependence is entirely captured in a phase factor like this. So you could doing that approximation, sticking in the stationary solution, you'll get this form. And what will happen is the r squareds will cancel, and you're left with this integral of just the initial wave function at t equals 0, integrated over all times. But if you think about it, that's just like integrating the density over all values of this argument in here. And that's this thing is just the incoming flux of particles, total number of particles times the velocity, and then this is the probability associated with the incoming beam of particles. So this is sort of like and so then this thing, if you recall, this thing, the thing that's left over here must be d sigma d omega, because the number of particles must be the flux times this d sigma d omega times d omega. And so that's another way to look at it. I did it last time with like an integration over r, but it was a little bit confusing because I forgot to add, the fact that this is the time dependent wave function. This is better. I mean, you see, you can change variables and change this into an integration over r, because r and t are in the same argument here. So you could take this v naught t and change this into an integration over dr instead, but it sort of doesn't, it's not so important. So I did it a kind of a different way in class, but last time, or 2 lectures ago, or what was it? No, I guess last time. But this may be a little bit more transparent. This expression, I think, is a little bit more transparent for what that probability is. So yeah, any questions about that? It's just another way of deriving the same thing, that even in the wave packet description, the scattering cross section is just the stuff that's left over. And you can kind of figure out what the, figure out what the units are. It's important. That's one way you can know that this has the right thing, because we know that this scattering cross section should have units of area. And if you look at the stuff in here, the way you can tell that it's a flux is you just look at the units. So the units of V naught are length over time. Then you have an integral over time. All right, so that gives you the time, and then you have this probability density squared, so that gives you units of 1 over L cubed. So you have overall units of 1 over length squared, and so then this thing has to have units of L squared to make sure that the final result is unitless. So has the right units of area. That's one way you can sort of check that things are working out properly. So you can see that this flux, in the sense, it's the number of particles per unit area is what it works out to be coming in the direction of the incoming beam. So that's like that incoming flux, number of particles per unit area. And then the rest of the thing must be the differential cross section. So hopefully it's a little bit more of a transparent derivation. But you could also just do it, the way I did it last time also works. It's just maybe a little bit less obvious how the units work. Okay, any questions about that? Okay, so I updated the scattering notes to include that way of doing things. So I like it a little bit better. It also fits better with the Bellac book. I also added the identical particle notes, which are also being sort of updated over time. And there's recitation today at 4. And there's no quiz. So, all right, so we're back to sort of identical particles. And that's sort of the topic we'll stick with for the rest of the class. And again, the idea was that when you have identical particles, well, you have a Hilbert space that's a sort of tensor product of however many particles you have in your system, say n of them. And then the key is that the label you assign to your particles can't possibly matter. So the state of the particle, if we switch around the labels, we take a pair of particle and we switch their labels, then the only thing that can happen to the vector in your Hilbert space is that it either picks up a minus sign or it remains the same. Those are the two possible cases, and that's sort of what we concluded last time. So you can actually define a kind of operator that's the pair exchange, or if you want the relabeling operator, or particle permutation, lots of ways to call it, where you just take the labels of the particles I and j and you flip them. So you call it particle label permutation. And one of the kind of important physical axioms that we have is sort of that any operator, any observable, will commute with the permutation operator. So any observable A has Pij A is equal to 0. And what that means is if you take any kind of symmetric state and look at its matrix elements with any kind of antisymmetric state, well, then you can conclude that no sensible operator will have matrix elements that connect these two kinds of states. It's another way of saying that there's no way any kind of quantum system is going to have transitions between fermions and bosons. And you can sort of see that from the commutation relation, because we know that for symmetric states that the symmetric state does not change under particle permutation. So we can add a Pij here that doesn't change. We can have this act over here that won't change the state. And so you have this, and then of course you can use this commutation relation to sneak the P past the A, and you have Pij acting on the antisymmetric state, but when Pij acts on the antisymmetric state, you pick up a minus sign by definition. So this becomes phi s A phi A. So you have this matrix element is equal to minus itself, and so the only possibility there is that it's equal to 0. So that's another way of saying that you can't have transitions between the two kinds of states. Another important thing, consequence of this, is that for fermionic states, they obey the Pauli exclusion principle. And we'll see the Pauli exclusion principle pop up in lots of ways, but the idea is if you have a state of two particles, say, and you label them A1 and B2, we know that we can't, this is not a proper state, right? Because it's not antisymmetric under particle exchange. If we exchange the labels, we get a different state. So we have to antisymmetrize these kinds of states. And so this becomes 1 over square root of 2, A, B minus B, A. And this is a convenient way of writing things. It's always implied that this is sort of particle 1 and that this is sort of particle 2. So if you have a state where particle 1 is in state A, particle 2 is in state B, then this would be the properly antisymmetrized state, right? Because it doesn't matter which one you call 1 and 2. So you have both. So you have to add all the combinations and make them properly antisymmetric. So now when you exchange the labels, that's equivalent to sort of exchanging these two things. The overall wave function, or the vector in Hilbert space, will pick up a minus sign. But you immediately see that if the two states are the same, then this whole state, which you call the AB fermionic state, then it just vanishes because these two terms will cancel each other. So a particle can't be in the exact same, two particles cannot be in the same exact quantum mechanical state if you have identical fermions. It's just not possible. And that's the consequence of this antisymmetry of the overall wave function. And that's just a statement of the Pauli exclusion principle. A very important principle. I don't know if I mentioned this, but when you touch a solid object like a table or something, why does it feel solid? Well, there's of course Coulomb repulsion between the electrons in your hand and the table, but also as you're pushing the two electron clouds into each other, electrons or fermions, you're trying to force the electrons in your hand and the electrons in the table to be in the same state. And so 50% of the sort of force that you feel touching a solid object is due to Pauli exclusion on top of 50% is just from Coulomb repulsion. It's kind of interesting. That was proven by Dyson, who, yes, is he still alive? I forget. He's quite old now. Maybe. No, he died last year, right? But yeah, Freeman Dyson, cool guy. Same Dyson as the sort of Dyson series we talked about earlier. Okay, so yeah, and of course, for fermionic states, you can extend the kind of anti-symmetrization to arbitrary numbers of particles. A convenient way to do that is to use the so-called Slater determinant. And that's just a convenient way of writing down all of the combinations that give you a fully anti-symmetric wave function. So for instance, if you want to construct a fermionic wave function for 3 particles, which would be you would have to add all the combinations of A, B, and C, so all the different ways of permuting among A, B, and C. And each time you permute these two, any two of them, you pick up a minus sign. Well, there's a convenient way of writing all that. It's in terms of a determinant. This whole thing is equal to 1 over square root of 3 factorial. That's just a normalization, because there will be 3 factorial different permutations of A, B, and C. So the normalization is always 1 over square root of n factorial, where n is the number of particles. And then you can write all the different combinations as a determinant that you would have to multiply out. And along the rows, you just write the wave functions for the 3 different states you're considering. And then along the columns, you write the particle identity, 1, 2, 3. And so that'll give you all the different ways of writing A, B, and C in different orders with the right minus signs attached. And that just comes from the rules of how you would multiply out determinants. So if you multiply this out, you'll get all the different combinations of particles 1, 2, and 3 being in the different states A, B, C. And the rules of determinants will give you the right minus signs, so that the state where you have particle 1 in A and 2 in B and 3 in C is going to have a relative minus sign to the one where particle 1 and 2 have flipped states. So particle 1 is in state B and particle 2 is in state A. So it'll keep track of those minus signs. And that's called a Slater determinant. Okay, any questions about that before we go to spin?
So for 2 particles, this is just the same as the wave function above, A cross B minus B cross A.
Sure. If I take this and dot it into R1, R2 to get the wave functions, I would get 1 over root 2 phi A R1, right? Phi B R2 minus phi B R1 phi A R2.
Okay.
That's the fermionic wave function. And you notice that that's just 1 over square root of 2, the determinant of phi A R1, phi A R2, phi B R1, phi B R2. All right, you would multiply these two together and subtract these two. So that gives us this. So yeah, it works for two particles. It works for any number of particles. Nice. More questions? And you can show that if A is equal to B for any of these, or whatever, if any of the two states are the same, then this whole thing vanishes. You can show that using properties of determinants, but it's not so important. So they just show you that there's a trick to get all the combinations, to get all the minus signs right. To get so of course for bosons, it's kind of like this determinant also, except whenever you see a minus sign, you just put a plus sign anywhere. So like you just put plus signs everywhere. So you can actually also kind of write the bosonic one also as a kind of determinant, except you would just take all the minus signs and turn them into plus signs for bosons. But otherwise, the counting is the same. So like for the 2x2 guy, you would just take the minus sign and turn it into a plus sign. That'll give you the bosonic one. Okay. Anything else? I'm going to clear this. Yeah, so even sort of thinking about states like this where you have a single label for the state, but in principle, you can have, for instance, an electron, right, which could be in like various states, various electronic states. Say it could be like in various states in a hydrogen atom, for instance, but it also has a spin, right? We know it's a spin 1/2 particle, so it's spin up has a two-dimensional Hilbert space associated with the spin. So when something is a fermion, its entire wave function, when you have multiple fermions, its entire wave function is what's antisymmetric, not just some portion of it. It's like the whole thing. So if there's any kind of internal degrees of freedom, like spin, then, well, you have to antisymmetrize both the internal degrees of freedom and any other kind of thing, like which spatial wave function it has, corresponding to an electronic state, say. And that's kind of a weird thing. And that's why, I mean, it's statements like that make the sort of spin statistics theorem difficult. It's a challenging theorem to prove, because what you're saying is it's the internal spin of the system that determines the statistics of your particle. That's why it's best left to sort of quantum field theory classes to prove. It's a hard theorem to prove. It's a very strong theorem, right? Spin statistics says that if you have half integer spin, then you're a fermion. And if you have a full integer spin, then you're a boson. But the fermionic and bosonic thing is a statement about like the entire wave function of your multi-particle state, saying no matter what kind of states you have in there, the wave function for the entire states, whether it includes spin and so on, and all that, must be antisymmetric for a fermion and symmetric for a boson. And the spin statistics theorem tells you that property is entirely determined by the intrinsic spin of your particle. So like an electron, is a fermion. So it's a little bit weird, I'd say. It's a hard theorem to prove. You can show that it's a consequence of special relativity. that the spin statistics theorem ensures that you have, it's a consequence of including special relativity in your quantum mechanics. So it's left for, relativistic quantum mechanics, which is a subject of field theory. Basically, if the theorem is violated, then you will end up breaking the rules of special relativity, and you'll have basically propagation of particles outside of their light cones, essentially. So but again, we won't prove spin statistics. It's a hard theorem to prove. Left for field theory, which is the relativistic theory of quantum mechanics. But okay, but we do have spin, and that's part of our state. And say for spin 1/2, we know what happens, right? Say we have 2 spin 1/2 particles. We know that the state of 2 spin 1/2 particles breaks up into a singlet and a triplet. We know this from our rules of adding angular momentum. We know that there's a triplet, which is total spin 1. And we know that the associated states are as follows. And again, when I don't put labels, I just mean that the first particle is an up spin, second one is down spin. And then there's a spin singlet state, which breaks up like this. So you see the spins already break up into 2 classes, right, that are symmetric and anti-symmetric. These guys are already all symmetric. If we exchange the identity of the spins, that doesn't change the wave function at all. And these guys are anti-symmetric. So you might say something like, well, electrons are fermions, so shouldn't they always, be in this anti-symmetric state? Well, no, because again, it's the whole state that matters and not just the state of their spins. So when you construct a state, a wave function for your, this is 2 spin 1/2 particles. When you construct the entire wave function, the fermionic wave function associated with 2 spin 1/2 particles, there's actually 2 possibilities. There's 2 ways you can make the wave function anti-symmetric. One way is you pick this anti-symmetric spin singlet state, and then the spatial portion that the portion of the state that corresponds to what energy level the particle is in, you would make that part symmetric, right? Because a symmetric wave function times an anti-symmetric one is still going to be anti-symmetric. So one possibility is you construct the symmetric portion for the spatial part here. And then the spin state can be in the singlet. Alternatively, if your electrons are in one of these spin triplet states, then you know that in order for the overall wave function to be anti-symmetric, then you know that the other states, describing the, say, energy level it's at in like a Coulomb potential, that that wave function has to be anti-symmetric. So the other possibility is that and then you can be in one of the symmetric triplet states. So those are the 2 possibilities. But you see, it's not so simple, again, because the point is that it's the entire wave function, including all degrees of freedom, that has to be antisymmetric, because you're actually switching the labels of the two particles. So if they're, in different orbitals or something like that, you switch those things too. So not only the spin or something like that. So if you want to create a fermionic wave function for two spin 1/2 particles that could be in two different electronic states, A and B, then these are the two possibilities. And you see, it sort of makes sense, right? Look, this is sort of explains how chemistry works, right? Because you can't put the two spins in the same electronic state. Say you can't have A is equal to B and have the spins be in one of these triplet states, because that would be aligning the spins in some direction. It would be the same spin state and the same electronic state. You can't have that, so the wave function vanishes, right, for this case. But here, the spin singlet state, the electrons are in different, they're pointing, or you can think of it pointing as opposite directions. The total spin here is 0, right? And in that case, you can have the electrons be in the same orbital. And that's actually sort of what happens is when you fill up electrons in different shells, your atoms, and you construct the periodic table, they'll fill up individual orbitals. Two electrons will fill up per orbital. So when chemists and stuff draw little orbitals, they'll draw little electrons, spin up and down, sort of filling up the orbitals from lowest to highest energy. And this is really the reason, right, is because if you're in the spin singlet state, you're allowed to be in the same orbital. You're allowed to have A is equal to B here. It's okay. So something to keep in mind. So let's see, what else? So you can think about, this actually has, this has consequences for the orbital angular momentum as well, because something to notice is that the P12, the particle relabeling operation, what will it do? If we have, for our two particle system, if we define a center of mass coordinate like this, and we define a relative coordinate, then this guy, so if we exchange the particle labels, right, S just goes to S, the center of mass doesn't change, but the relative coordinate does change from R to minus R. And remember that spherical harmonics, they have an important property, namely, if you evaluate a spherical harmonic for minus some r hat direction, remember, spherical harmonic depends on sort of orientation, theta and phi. If you take minus that orientation, then this is equal to minus 1 L YLM, the original orientation. So you pick up a minus sign whenever you have odd L. And so if you think about expanding these spatial wave functions in sort of spherical harmonics, you see that you can't have, if you're in the spin singlet state, you better have L be even in your expansion, because if you have odd L, that'll pick up a minus sign, which you can't have, because we know that the spatial part has to remain symmetric under particle exchange. So it means that if your electrons or spin 1/2 particles are in a singlet state, So if you are in one of these spin singlet states, then the only contributions to the orbital angular momentum must come from even L. And conversely, if you're in the triplet, then we know that the spatial part of the wave function must be antisymmetric. Then that means that the orbital part, remember the orbital angular momentum has to do with the spatial wave function, right? So the even or oddness of the spatial wave function is determined by the angular momentum at the spherical harmonics. So if you have a spin triplet, then you must have odd L. And that's pretty powerful. It's powerful constraint on the angular momentum, right, of two identical particles. You can actually see that in spectroscopy. I'll talk about that in a bit. Anyway, so for two spin 1/2s, there's also a special notation that's used to sort of describe the states of your particle that include the spatial part, the orbital angular momentum, and the spin, and so on. And it's usually denoted like this. There's a 2s plus 1 number here. Here, there's the orbital angular momentum, L. And then here, this is the total angular momentum. And this is the orbital. And then this is the spin part. So the total spin. So for instance, if you're in a spin singlet, then this quantity is 1 because the singlet has total spin 0. If you're in the triplet, then this thing is 3 because then the total spin is then 2s plus 1, is 2 plus 1 is 3. So, and the L's, the orbitals are labeled by, depending on the value of L, they have different letters associated with them. This one is called S, this one is called P, this one is called D. So you can specify the states of two spin 1/2 particles with this funny letter, with the superscript and subscript. So for instance, here's 1s0. This guy would be something with 0 angular momentum, orbital angular momentum. It would have 0 total angular momentum. And it's 1 here, so that means this little s must be 0. So this is the spin singlet. This is this state for the spin and the state with 0 orbital angular momentum. So that would be one possibility. Another example would be 3p2. This is a total angular momentum of 2. 3 means that we're in the spin triplet state, right? Because s must be equal to 1. And this means that we're in the L is equal to 1 state. So this sort of fully describes the sort of rotational, the orbital angular momentum and the spin angular momentum states for two spin 1/2 particles. It's used frequently in chemistry. So that's for two spin 1/2s. Of course, for two spin 0 particles, it's very easy. For spin 0, that's a full integer. 0 is an integer. So that must be two bosons. That's two bosons. So for two identical spin 0 particles, you always have even L, right? Because then your wave function has to be symmetric and there's no spin part to even consider because it's spin 0. There's no multiple states that you can have. There's no spin up, down. That's it. There's just spin 0. No spin. So that means they're bosons, and the orbital angular momenta that it can have only has even L quantum numbers. Let's see, that's weird because, you know, if you have two non-identical spin zero particles, well, then they can rotate around each other however they want. You can have any orbital angular momentum quantum number. So it's kind of interesting that identical particles actually forbid certain orbital angular momenta because of this property that you have to either symmetrize or anti-symmetrize the total wave function, depending on whether it's a fermion or a boson. So pretty cool. Any questions about these two examples? You can also do this in general, so I'll do next. So again, the point is whether or not the spatial part is symmetric or anti-symmetric is really in 3D entirely, you can do it in spherical coordinates, is entirely determined by the spherical harmonic expansion, because if you move to these relative coordinates, what happens is that the orientation of the relative vector, pointing between the two identical particles, that's what picks up the minus sign under particle exchange. It's just the relative position of the two things, right? It just picks up a minus sign. And so the consequences of this reflection, it's just entirely captured by the spherical harmonic. Basically, if you reflect the relative orientation, your overall wave function either picks up a minus sign if that component of it has a even or rather an odd L, or if it's an even L, then it stays the same. So that's why the sort of selection rules for which for the spatial part are given entirely in terms of like which orbital angular momentum quantum numbers you can have, because that's the thing that picks up the minus sign when you do the particle permutation, right? Because the sort of radial coordinate, the magnitude of it doesn't really matter, right? That's just sort of the distance between them that doesn't change if you exchange them. And also their center of mass coordinate doesn't change, right? When you flip them, because they're identical. So, if you flip them, then that doesn't change the center of mass because, they're the same mass. All right. Any questions though? This is a pretty important concept, this interplay between spin and orbital angular momentum. Okay. So what's the general case? In general, you could have an arbitrary spin, of course, doesn't have to be spin 1/2, could be anything. In general, there's a total spin, which would be a combination of the spins of the two individual particles, the identical particles. And they're identical, so of course it's the same spin. So the quantum numbers that F can take on range from 0 to 2s, where s is sort of the spin of that identical particle. So it's like two identical spin s particles. But we know more. We know about what happens when we add the spin to the orbital angular momentum, right? We know that, the total spin is going to be, of course, F plus L, the orbital part. And we know how those things add because we studied addition of angular momentum. We know that the way in which these things add is described by the Clebsch-Gordon coefficients. And so we have Clebsch-Gordon coefficients that tell us about how that tell us about how to add these angular momentum together. And the Clebsch-Gordon coefficients have an important property. They actually tell us about what happens under particle exchange. Remember, how do we add? So there's, if we add the individual, yeah, so if we have angular momentum states L1, M1 that we're adding together to L2, M2 to get a total angular momentum state Jm, these Clebsch-Gordon coefficients have a particular symmetry, namely that they pick up a minus sign under exchange of L1 and L2 and M1 and M2. And the minus sign is given by this -1 raised to L1 plus L2 minus J, the total angular momentum. And this is L2, L1, now M2, M1, Jm. So that's what happens under exchange of L1 and L2. And so for us, what we're concerned with, of course, is adding spin 1 and spin 2. So for us, L1 and L2 are just the spin S. So for us, it's like S, S, right? We're adding spin S to spin S. That's this guy. And M1, M2, Jm. And so this minus sign is just going to be, what is it? It's going to be 2S, right? And then there's going to be the total angular momentum, and this is for the spin, which is just F. So this is the minus sign that it picks up. It must be twice whatever the spin is for the two identical particles minus F, which is the total spin. So like for our spin 1/2 guys, S is 1/2. So it'd be 1 minus the total spin, which is either 0 for the singlet or 1 for the triplet, right? And if it, so it's 1 minus 0 for the singlet, and we pick up a minus sign. And otherwise, we don't. And that makes sense because the singlet is the one that's antisymmetric, right? So this tells you what happens under what happens to the spin state under particle exchange. It generalizes the idea of the singlet and triplet, right? That for the singlet, we know that we pick up a minus sign. For the triplet, we don't. This generalizes that property to arbitrary spin. So there we go. And I guess I shouldn't call this J, I call it F, right? This is the total spin. Okay, so that's the property. And so now we know what to do, right? It's the same as the singlet and triplet. We know that if the spin part picks up a minus sign, then we must make the orbital part, the L part, we must make that either symmetric or antisymmetric, depending on whether the identical particles are half integer or full integer spins. So that's pretty powerful. This gives you, for arbitrary spin, it tells you if the spin part is going to pick up a minus sign under particle exchange. So again, the example that we had already is S is equal to 1/2. So then there's two possibilities for F. It's either 0 or 1. And in one case, we have -1. 1 minus F is equal to -1. So it does pick up a minus sign under particle exchange. That's the spin singlet. Otherwise, we have -1, 1 minus 1, which is just 1. And that's the spin triplet. Now you could do the same trick with any spin that you want. I mean, here S equals 0 is really easy because then the only possibility is F is equal to 0, and then you just have -1, 0 minus 0. That's just 1. So always symmetric. Spin 0 always has a symmetric spin wave function. Now you can generalize this to what have you, to whatever you'd like. So like spin 1, of course, so those are bosons. F then ranges from 0 to 1 to 2. So see, it's not so obvious. Now it's -1. Now it's 2 minus F, right? So for these two states, you have symmetric. You'll have symmetric cases. You have symmetric wave functions, spin wave functions, but for this guy, it'll be anti-symmetric. So that means if you're in total spin state 1 for 2 spin 1 particles, then your spatial wave function must actually be anti-symmetric to cancel the anti-symmetry of the spin part. It's kind of weird, right? So just because you have 2 identical particles that are, integer spin doesn't mean that their spatial portion of their wave function has to be symmetric. Could also be anti-symmetric. And the same thing for fermions. You can have either symmetric or anti-symmetric spatial wave functions. It depends on the spin state, because it's the total wave function spin plus the spatial part that has to be either symmetric or anti-symmetric. So that's the important thing. Okay, any questions about that? The Clebsch-Gordon? Okay. So yet another, I guess I'm kind of running out of room here. I'm gonna clear this. So that's the general case. So we looked at 2 spin 1/2, 2 spin 0s. This is the general case. Okay, so I'm gonna clear this. So this actually has important consequences for just observable things, like, for instance, rotational spectra of hydrogen molecules. If you have 2 hydrogen atoms here, and you think about this, the rotational spectra of this little bar, we know that the energies associated with any kind of diatomic molecule, I guess we saw it's a quantum rotator, right? It's just something that rotates around, just has the rotational kinetic energy. The energies associated with that are h² / 2i times j plus 1, where j is the angular momentum quantum number for that rotation. Well, what's interesting is that because of this property that the hydrogens have to obey, if they're, because they're identical, they have to be, either obey fermionic or bosonic statistics. This actually has a consequence on the rotational spectra. You don't actually get all of the rotational energy levels because some are forbidden by the by the statistics of the particles. And so what's important to consider is that the nuclei of these hydrogens, the protons, they're actually also spin 1/2 particles. And so they are fermionic. And so the total wave function has to be anti-symmetric. And so for spinning hydrogen molecules like this, there's again 2 possibilities. Either the total spin is 0, that's the spin singlet. And this is for the nuclear states now of the hydrogens, of the protons in here. They're spinning around each other. The nuclear spin. Either the nuclear spins are in a singlet or they're in a triplet. And in the case of the singlet, you know that the spin part is already antisymmetric, so only even J can contribute to the rotational spectra. And in the case of a triplet, only odd J can contribute because the triplet is symmetric. So, and those are two different kinds of diatom. Those are two kinds of molecules, and the only difference is the nuclear spin states. It's amazing because you would think that something like as macroscopic as a rotational spectra shouldn't really depend on what goes on with the nuclear spin states, but yet it's true that depending on the nuclear spin state, which is actually also very stable, right? Because it's sort of confined in the nucleus, it's hard to transition. It's hard to transition from the singlet to the triplet. You need some kind of something like a thermal fluctuation or something typically won't be enough to transition you between them. So it's a pretty stable thing. You're either going to be in the singlet or the triplet. And you can take hydrogen gas, for instance, and calculate its rotational spectrum. You'll see it's consistent with a certain distribution of molecules in either the singlet or the triplet state. So it's a sort of, it's very important in the statistical mechanics as a common example that's given when you study quantum statistical mechanics. But we won't really talk too much about it. But just so you know, this one's called para hydrogen, and this one's called ortho hydrogen. And they're two different kinds of molecules. They have different rotational spectra. And what's interesting is, of course, so the nucleus, so for the hydrogen is 2 protons. What you can do is you can add a neutron to one of them, make it heavier, and this would be an HD molecule. And that immediately ruins this because now you no longer have 2 identical nuclei spinning around each other. This one, is heavier. It's deuterated, as they say. And in this case, all J will be allowed. So you get back all of your other rotational modes. And that's a very different spectrum, right? So like the ortho hydrogen rotational spectrum will be spaced like this, and then the para hydrogens will just sort of be in between the even ones. But then as soon as the 2 nuclei actually become distinguishable, you get back all the J quantum numbers. Of course, the spacing will be different because your moment of inertia will change, but still, it's interesting. You lose the selection rule. So that's one example of where this really has a significant difference, an observable difference in the sort of behavior of molecules, sort of macro scale. This rotational spectrum is something that's sort of relatively easy to measure. The other place where you can use these kinds of reasonings to make some conclusions is you can actually use this to understand magnetism and the way why magnets exist, or for that matter, not only sort of ferromagnets where which align their spins, but also antiferromagnets which have electronic spins that are anti-aligned. So the way you might think about it is if you have a solid or something, and you have 2 electrons in the solid, they're identical particles. And so we might wonder what kind of states they might have. And we know that when the two sort of neighboring electrons, say they're in the triplet state, right? What would that mean? That would mean that their spatial wave function is antisymmetric, right? The triplet is the one that has symmetric spin. So that must be an anti-symmetric spatial wave function. And what would that look like if I were to like draw their wave function, you know? Well, it would be anti-symmetric relative to, their relative distance between them. So it would look something like this. And if we think about this kind of wave function, we notice that since it's anti-symmetric, it goes through 0 here between them. And that means there's very little probability, right, of finding the electrons here between them. And so the anti-symmetric shape here, it kind of minimizes, and of course these electrons repel each other. There's a Coulomb repulsion. And having an anti-symmetric spatial wave function is a way of minimizing the Coulomb repulsion, simply because of the anti-symmetry of the spatial part, right? You don't find the electrons in that region between them because of the anti-symmetry of the spatial portion of the wave function. But there's, of course, a price you pay, namely that because the wave function has to sort of jump through 0 here and be anti-symmetric, the price you pay is that this gives you a large gradient. And we know that the momentum is proportional to the gradient squared. So the sharper the variations are in the wave function, the larger kinetic energy you have. So there's a kind of trade-off that you can minimize Coulombic repulsion at the expense of having higher kinetic energy. So what does this all mean? It means that if you're solid, if the electrons in your solid want to minimize Coulomb repulsion, one way they can do that is by going into a triplet state where the spins are aligned. And that would lead to a situation where their spatial wave functions would have to be anti-symmetric, which minimizes the Coulomb repulsion at the expense of having a larger kinetic energy. And that's very hand-wavy explanation for why you might get a ferromagnet where the spins are all aligned. Very, very hand-wavy, but it kind of works actually. And you can also use the same reasoning to explain a antiferromagnet. So if, for instance, you don't care about the Coulomb repulsion, you want to just minimize the kinetic energy, say, well, then a good way of doing that is to go to the singlet state, where the spins are anti-aligned. And that would be an anti-ferromagnet. And what's the advantage of that? Well, then the spatial wave function has to be symmetric. And what it might look like is, something like that. Be a symmetric wave function. And this is great because, well, now there's more probability density. You can have a non-zero probability density between the electrons, but that's okay because this has a much smaller, flatter, so it's a smaller gradient. So you can gain on the kinetic energy. You can have smaller kinetic energy in this case by forcing your spins into a singlet state where they're anti-aligned. So depending on whether or not you care about minimizing the kinetic energy versus the Coulomb potential energy, you could force the spins to either, want to align in the case go into these triplet states. That would be case of a ferromagnet, or if you care about having small kinetic energies, then you could force your spins into these singlet states where they're anti-aligned, the neighboring spins in a solid. And that'll depend on the solid, depend on the properties of the solid. But that's at least a very hand-wavy explanation using identical particle statistics of why solids can be ferromagnets or anti-ferromagnets, which is hard to understand, otherwise, why would you get an anti-ferromagnet? It's very strange to think about using just purely classical intuition. But, so it goes. Any questions about that? It's very hand-wavy, but, a more sophisticated argument would just add more math to this, but the basic idea is sort of the same. Again, it's a trade-off. You have identical particles, in this case, electrons. Aligned spins, same spin state, means you have an anti-symmetric spatial wave function. Anti-aligned spins, as in a spin singlet state, means you have a symmetric wave function that has different consequences for the spatial part of your Hamiltonian, right? Which is composed of a Coulomb interaction and a kinetic energy. Different trade-offs. In one case, you get more kinetic energy. In one case, in a smaller Coulomb repulsion. In the other case, you get a smaller kinetic energy, but a larger Coulomb contribution. So it's kind of fun to think about the interplay between that. And it's a consequence of the identical particle statistics of the electrons. So, okay. So those are the examples. Now we're gonna talk more about sort of properties of identical particles, and in particular scattering, sort of tie it back to what we just talked about. But any questions about this idea? All right. Hopefully it makes some sense. What's going on? So we can think about scattering of identical particles, and that's kind of interesting too, right? Because we don't know which particle is which after scattering. So how would you would take two identical particles, right, and you'd smash them against each other, and then they would come out, and you would detect them with some pair of detectors out here. And the idea is you don't know which one's which. So one of two things can happen, right? Either this particle comes in and this one comes in, and then this guy turns around and heads off that way and gets detected, and this guy turns around that way, gets detected. But there's an equivalent possibility that this guy comes in this way and this guy comes in this way, and then this one decides to go up there and this one decides to go down here. And because they're identical particles, there's absolutely no principled way of distinguishing between those two possibilities. And so in fact, those two possibilities will interfere with each other quantum mechanically. The amplitudes for those processes will add and lead to the possibility of either constructive or destructive interference. So if the particles are not identical, so suppose they weren't identical, well, then you could distinguish between those two different kinds of paths, right? And so then in the case, you'd have a distinguishable cross section, and that would you would just have to add up the probability of being detected either from the orange path or the green path, and they'd be distinguishable. So you just have to add the probabilities because those are distinguishable, measurable differences in the scattering process. So what would you do? Well, you would integrate over the probability of all the different ways of placing these top and bottom detectors for the total cross section. Of course, you want to integrate over only a half sphere because we're just assuming we're measuring all the different orientations of those two detectors which live along the line. So the total probability, or the total cross section rather, is just going to be half of the integration over a whole sphere, and it's just due to the fact that there's two detectors. And it's just going to be a sum of the probabilities associated with those two kinds of scattering processes. And if we think about for a single particle, the differences between the orange path and the green path is just a factor of pi minus theta, right? So if for the orange path you have a scattering amplitude associated with some theta scattering angle, then the green path is also a scattering amplitude, but with a different angle, in this case, pi minus theta, right? It's 180 degrees minus theta. So those are the two different kinds of scattering amplitude that correspond to those two different paths. So, and you would just add up their amplitude squared. And those you would just add up. That would be it. That's just the two different ways in which the particles can scatter. And if we don't care about which one, we would just add the probabilities like this, right? They're distinguishable, so we can tell the difference. And if we don't care about the difference, then this would be just the total cross section for the scattering. It's the sum of the two ways for the particle to go, either this way or this way. But if they're identical, then there's no way, even in principle, in which we can distinguish between those two cases. And in that case, well, you would have interference. In that case, your cross section, again, integrating over all the detector directions, you would have to add the amplitudes together because both of those processes will interfere. So there'll be, of course, a cross term that describes the interference.